have more information. Let's say you know that a user would like to watch a movie when the weather outside is cold or something like that. So you have contextual recommendation. Or a parallel in the image restoration problem would be you have a sequence of frames, which is basically a video, and you would like to restore the video. So here the language of matrix is insufficient, and you would have to go to tensors. Basically, a tensor, in case you do not know, is a multi-dimensional object. And just like how you use matrix factorization, you would want to use tensor factorization to solve this problem. So, but we are especially worried about the cold start problem, which was discussed by the previous team. And here is where side information can help. So when you have a completely new user or you have a completely new movie, what do you do? So let's say you have external information that says, for example, you have a social network amongst the users. So you know that a user is friends with certain users. Or you know you have a description of the movie. You know which director, who's the director or who starred in this movie and so on. So you essentially can do better. So what are we really interested in is a tensor completion method. But then that's kind of straightforward. You do tensor factorization. But what we really want to do is to make this, since it's a tensor completion method, it's naturally general in terms of the dimensions. But what we are really contributing in this project is how we can incorporate side information and how thereby you can resolve the cold start problem. And then Kijong will explain the algorithm, and then Hemant will explain the experiments.
I will briefly introduce tensor and tensor factorization, then I will introduce our proposed tensor factorization method. Tensor is a high-dimensional array, and it can be thought as a generalization of vectors and matrices to higher dimensions. This is an example of three-dimensional tensor, and it can be used to model three-dimensional data like time derating data and video. This figure shows matrix factorization, where a given matrix is approximated by the product of two low-rank vector matrices. Tensor factorization is a generalization of this for tensors, and as seen in the right figure, a given tensor is approximated by the product of three low-rank vector matrices. These graphical models compare generative processes of previous method without corner and proposed method with corner. In the previous method, on the left, each latent vector is generated independently from given distribution. However, in proposed method, corner matrix, which defines correlation between latent vectors, is used to generate latent vectors. One advantage of our method is that our method can deal with cold start problem. So let's imagine a new user without any rating data. In the previous method, we cannot estimate the latent vectors of the user at all. However, in proposed method, we still can estimate the latent vectors of the user based on the corner matrix, which measures the similarity between users. So of course, the objective function is the log of the posterior probability, and we use the stochastic gradient to maximize this. However, we still have a problem. How can we define corner matrix? So to define corner matrix for users, we use side information. From social network, we compute the average commute time of nodes in a graph as a corner function, and we also used language similarity of reviews that users wrote. To define corner metrics for movies, we also use side information. Specifically, we measure the similarity of the plots and other attributes of the movies. And we also combine this with graph corners to specify corner metrics and save computation and space usage. And for other dimensions, we use RBF corner, which first is a spatial and temporal smoothness. Yeah.
Okay, so for our experiments, we can conduct our experiments on 4 publicly available data sets. So the first data set was Flixster, which is a movie rating database. It has which users rated what movies at what time and it also has the social network information. A second data set is very similar, opinions, where users, instead of rating movies, rate items. And the third data set is the beer advocate data set, where users are rating beers. We do not have any social network in this, but we do have a lot of aspect ratings, which could be used to compute similarity between users or kernels. And a fourth data set is video restoration, for a video restoration problem, where we take 10 images and manually corrupt some of them and try to see if our method works well and is able to restore the video itself. So this is a result for Flickr database. On the leftmost figure, you could see that this is for the overall. This is not for the cold start problem. We are not actually doing, and the blue line denotes the no kernel baseline, and the orange line is our method. So you can see that in the leftmost figure, we are not getting any improvement over the baseline. However, when we move to the cold start evaluation, how is our method performing better for cold start problem instead of the in comparison to the other baseline, we could see that when our method has to predict new context, user, and movie, all three together, we are doing much better. And similarly, just for new context, we are clearly doing a lot better than the baseline algorithm. For other data sets, beer advocate and opinions, we are receiving similar results as Flickr. So for the video restoration data set, you could see the top left is our original video that we constructed. And we corrupted some of them as you can see in the top right. Some